So, in Newton's third law, we learned that forces work in pairs. They're equal in magnitude, opposite in direction. And so, what we're going to do now is we're going to draw these as diagrams to help us understand the interaction between forces. And let's start with one that we did back when we talked about friction. We talked about normal forces. So, if you recall, what we talked about previously was that if we have an object and it's got an influence of gravity, let's just say that this has a force of 15 newtons. It's the mass times the acceleration, and it has a gravitational pull of 15 newtons downward. Okay, and that's our FG. And what we know is that we also have a force upward that I told you was going to be equal, just opposite in directions, and we called that the normal force. So let's talk about what that is and what's going on. Well, there is a surface in here, and what's happening is that the reason that nothing is moving is because the table is pushing up, and that creates this surface between the two objects. Okay. And so what we see is that our normal force and our force of gravity are equal. Well, let's talk about what happens if they're not equal. What would happen if the force of gravity was greater than the normal force? Well, if that was the case, then the table would break. Okay? Because this is pulling down so hard that the table cannot support its weight. And so, therefore, the table would break. Okay. What about a second scenario? What if the normal force was bigger than the gravitational force? Well, this is impossible as well. I mean, what we would see is we would see this object float up into space. Well, that doesn't happen. Okay. Um, it'll float away. Okay. So, what we're seeing here with our normal force is that the normal force is going to be equal to the gravitational force, just opposite in directions. Okay. And these diagrams are referred to as free body diagrams. And we need to be able to get practiced at these things. So, free body diagrams. Okay. Once again, remember that gravity always pulls the object down towards the center of the earth. And the key piece of the normal force that it is perpendicular to the surface. Okay. Key point. Okay, we talked about the normal force in gravity, that's the up down. But what about a sideways force? So here I am, I've got a string, I've got it pulled tight. You can see it's pulled tight here, and I'm going to pull it horizontal to the floor or to the desk. And I'm pulling, but I'm not applying a huge force. It doesn't have a huge force. Why? Why isn't it not moving? Well, there's friction pulling it back in the opposite direction. So I'm not pulling hard enough to overcome the friction. Let's see if we can draw a free body diagram for this book. So here I have my table, and I've got my green physics textbook on it. And as we previously discussed, what we have is we have a downward force caused by gravity. We have this equal and opposite force called the normal force, which is the table holding the book up so that it doesn't fall to the floor. What I then did is I then used some kind of horizontal force to the desk, and I'm going to call this A. This is an applied force. Applied meaning that I pushed it somehow, okay, or pulled it. And then what we have is we have in the opposite direction is this force of friction. which we previously talked about. Okay? So remember that our normal force is going to equal our force of gravity, just different directions. Okay? So now what we're looking at is we're looking at the applied force compared to the frictional force. If the applied force is bigger than the force of friction, then the book slides in the direction of the applied force, that way. Okay? If the force of friction is bigger than the applied force, it doesn't move. Okay? The book does not move. We cannot have a force of friction that is greater than the applied force. The worst it can do is be equal to. So the book does not move. Because this really doesn't happen. Okay? But if the force of friction equals the force applied, the book does not move either. Okay? This, once again, is a free body diagram representing the pulling of the book. What we need to look at is what is referred to as our net force. And this is an overall picture of what happens. And if all the forces are equal, the book does not move. If the forces are unequal, the book might move in one of the directions. Usually it's the direction of the applied force. So now what I have is I've built a ramp here, and I've got my textbook on it. Here we are. It's not moving. Free body diagram, it's not moving. What do we know about the forces? I want you to pause the video, see if you can figure it out, and then I'll show you the answer. This time what I have is I have a ramp. I have a book on the ramp. Okay? Because it's not moving, we know that the forces must all counterbalance each other. We have a force of gravity. What we need to remember is that gravity is straight down. Okay? It's caused by the mass of the book, but it's straight down. This is where most students make mistakes. The normal force is that way. Oops, FN. Okay? Once again, it is perpendicular to the surface. It is not here. That's what most students want to do, is they want to put it upward, but it's not. So we're going to have to do some math to figure this out. We'll come back to that another time. Then what we have is we have something pulling it down here, whether it's me or maybe it's gravity moving it down here. This is the applied force, and the friction opposes the direction that the book wants to move. This is the force of friction. So here's another free body diagram that I want you to draw. So instead of having a ramp, what if it was straight up, like a wall? Okay, I've got my beautiful orange cabinets here. But if I'm going to take the textbook and I'm going to push the textbook into the wall, I'm not pushing it up. I'm pushing it in, straight in. Okay, so I'm pushing it straight into the wall. Let's see you draw a free body diagram for that one. Pause the video, see if you can get it. Check your work in a moment. I've not had many students get this question right. It's not that difficult of a problem. So what we have is we have the book, that's the green, being pushed against my orange cabinets. So which direction did I push? Well, I was pushing in. I was pushing into the cabinets. We could leave it drawn out like that, but I love drawing it from the middle of the book out. So this was how I pushed. That is my applied force. Okay? We also had a force of gravity. Remember, the force of gravity is always going to be towards the center of the earth. So in this case, the book wants to go straight down. Okay? What was preventing it from going down? Well, we had a force upward. Most students are going to tell me that, this is the normal force because that's gravity. That's going to be the normal force. But no, it is not the normal force. this is my frictional force. Okay, the frictional force is in the opposite direction that the book is trying to move. The book wants to move down because of gravity. Why is it not moving down? Because the friction is holding it upward. It is in the opposite direction of the way the book wants to move. We also have a force here. We have to have a force here to oppose the applied force. Once again, this is the normal force. Remember that the normal force is going to be perpendicular to the surfaces. And the surface of the book and the surface of the cabinet is right here. So the normal force is perpendicular to that. So once again, to summarize, because the book was not moving, we had equal forces. The force of friction was holding it up as the force of gravity was trying to hold it down or pull it down. The applied force is how hard I pushed it into the wall. It equaled the normal force. If the normal force was not big enough, then I would have pushed it into the wall. It would have gone like through the cabinet door, but it didn't. So the normal force and the applied force must be the same. How did you do with that question? So here we have an object with a mass of 6.2 kilograms placed on a flat, level table. And we're going to give it a pull. I didn't put the direction here, but I'm going to give it a pull here, an applied force of 15 newtons. I've got the coefficient of friction, 0.3. And I want to know, will this thing move? If so, what direction? What is the overall forces? And can we draw a free body diagram? So I've got my applied force already on there. I know that friction opposes the direction it's trying to move. I know that the gravity wants to go downward. And I know that the normal force is perpendicular to the surfaces. So there's my free body diagrams. These are vectors, and they should be drawn to scale. So I'm going to have to look at that in a moment. So now let's start by calculating our force of gravity. Our force of gravity is mass times acceleration, or more specifically, it's mass times the force of gravity. So in this example, we have 6.2 kilograms multiplied by 9.81 meters per second squared. And that's going to give us a force of gravity of 60.822 newtons. And that is in a downward force. For reporting it here, I'm going to write it with a number of significant digits. My upward force is equal opposite directions. So my normal force is a 61 upward. So these arrows should be about the same length. They look pretty good there. Now I'm going to, I'm looking at this applied force here. I already know that that is way too long. So I'm gonna shorten this a little bit because my arrows should be sort of equal. And this one should be about a quarter of the length of the other, right? If that's 60, that looks a little bit more like a 15 force there. Okay, so now the question is, what does my force of friction look like? And what we know is we know that mu is the force of friction compared to the normal force. So we can find that the force of friction would be equal to mu times Fn. And we know that Fn was 60.8022. So this would be 0.300 multiplied by 60.822 newtons. And what we're going to learn from that is that the force of friction is 18.2466 newtons. Rounded off to the proper significant digits, we're looking at 18 newtons. So going back to my free body diagram, once again, I drew that one a little bit long. I'm going to shorten this up. But what we're going to see is that the force of friction here is 18 newtons. And my net overall is my applied force is not big enough to move this object because this is a bigger force. So the book does not move. We have a 900-gram object. It's on a flat horizontal surface, and it's pulled with a force of 7 newtons. The coefficient of friction is 0.152. And what I want to know is, well, first of all, we need to draw a diagram to represent this. But does the object move? And if so, what is the net force? So let's start by drawing a diagram. So I've got here's my flat horizontal surface, not the best one ever. Here's an object. I'll put a little box on here. Okay. And now I'm going to draw a number of forces. Okay. I'm going to put my FA to the left this time just to be different. My FA is 7 newtons. Okay. Friction is opposing that. I have a downward force due to gravity. And then I've got this upward force, which is my normal force. So there's my free body diagram. I may have to change the lengths of the arrows to make sure that it's all in perspective. So next up, let's find the forces. I'm going to always start with force of gravity. So I'm going to take my object, which is 0.9 kilograms, multiply that by the force of gravity, 9.81 meters per second squared. And I'm going to find that my force of gravity here is 8.829 newtons. Okay. I'm looking at 3 digits, so how about 8.83? 8.83. Okay, my normal force going up will also be 8.83 upward. Okay, now find my force of friction. Force of friction is mu times Fn. So that was 0.152 multiplied by my Fn, which was 8.829 newtons. And now I'm going to have a frictional force equal to 1.34 newtons. Oh, I'm going to change the length of that arrow. It's just a little bit too long. If this is 7 and that's about 9, that looks pretty good. But this one's a little bit too long. I'm going to shorten that up. Okay, so our force of friction is there. And this is a force of 1.34 newtons. Okay, so there's my free body diagram completed. Does the object move? Well, yes. It's going to move. And in my diagram, it's going to move in the direction of the applied force. So I'm going to say to the left. Okay, it's going to move in the direction of the applied force. And that's because the applied force is greater than the frictional force. So it's going to move to the left. What is the net force? Okay, well, the net force is where we sort of do our vector analysis of all the forces. And what I'm seeing is that the up and down, the force of gravity equals the force normal. Okay? So there's no net up or down. But what I'm also seeing is that FA is greater than FF. How much greater is it? Well, if I subtract those, so if I said FA subtract FF, I'm going to see a difference there of 5.66 newtons. Okay? This is my net force. That is my F net. 5.66 newtons left. Make sure we get our direction in there, really important.